Aircraft accident rates are very low, but this was not always the case. Aircraft accident rates peaked in the 1970s and have been driven down in the last 50 years, even with a dramatic increase in the number of flights. Aircraft accident rates were so high in the 1950s and 1960s that only 20% of Americans were willing to fly 104. Bill Boeing realized that if he was to build a successful industry, accident rates needed to improve dramatically. The ensuing effort has been remarkably successful. That success was a result of focusing on all aspects of reducing risk. Aircraft operate in widely differing and very challenging environments. At the same time, high risk is simply unacceptable. The approach used today for safety in commercial aircraft recognizes this reality. Conservatism and a slow pace in basic design changes has allowed learning from experience and developing the science underlying aeronautics. The industry has emphasized the use of well-understood and debugged designs to maintain and enhance safety. Occasional major technological developments, such as the jet engine, the introduction of computers into control, and structures made of composites, introduced new hazards but also eliminated others. For example, jet engines are much simpler than older types of engines in terms of needing fewer controls and fewer components. In addition, they can sustain larger amounts of damage before complete failure. Improved jet aircraft technology provided increased speed, efficiency, and safety. Also, improved cockpit interfaces and standardized training practices and operational procedures have had major influences on safety. On balance, such developments usually reduce accident rates or at least particular types of accidents. Except for the disruptive effects of these new technologies, the hazards have not changed significantly. Until relatively recently, accidents were assumed to be caused by failures of the aircraft components or pilot errors. The pace of technological change is increasing, however, and new design features are being employed, such as the use of fly-by-wire systems, automated flight controls, and some unstable aircraft features. The increased pace of change is partially driven by competitive pressures to introduce advanced control features and reduce fuel consumption. One result is that the causes of aviation accidents are also changing. When a new aircraft design is created, it is analyzed to identify failure scenarios that could lead to a hazardous state, and then those scenarios are used to guide the designers in attempting to eliminate losses. Because there is often no safe state to move the system into, in contrast to nuclear power, where the nuclear reaction can be shut down. Focus has been on preventing and tolerating failures and errors using design integrity and quality, component reliability enhancement, safety margins or factors, redundancy and backup systems, design for checkability and inspectability, error tolerance, or designing such that common human errors are easily identified and corrected or do not have catastrophic results. For example, in the design of cockpit layouts and switches, or the use of color coding or different shape connectors in W1R1 DIN, failure warning and indications to human operators, as well as providing information about the current state of the aircraft. Failure containment, which involves isolation of components or subsystems so that failure in one will not affect others. Damage tolerance or designing so that surrounding failures are tolerated in case the failures cannot be contained. Designed failure paths. When high energy failure cannot be contained or tolerated, but it can be directed to a safe path. An example is the use of structural fuses in pylons so that the engine will fall off before it damages the structure. Flight crew training and specified flight crew procedures to prevent common errors and for use in situations where there is not enough time or information for human operators to figure out what to do themselves. Incorporating human factors, engineering as an important part of design, particularly the design of cockpits and of piloting and maintenance procedures. Beyond these general design strategies, there are also specific airworthiness criteria, including the design of seat belts, oxygen masks, and systems in case of rapid cabin depressurization, escape and evacuation procedures, and equipment, life vests and rafts, and so on. Many of these designs have been improved after accidents showed some of the assumptions used in the design were flawed. As underlying scientific knowledge about flight, materials, and propulsion was developed, this knowledge was used to design safety into new aircraft and to prevent physical failures and design errors. In addition to basic design techniques, operability and safety during operations are major considerations in the design process, such as creating practical functional check procedures that can be used to determine a component's condition and its ability to perform its intended function. Such design for operability and maintainability includes periodic inspections, for example, of the aircraft structure and engine rotor discs for fatigue damage. But the design of the aircraft itself is only a small part of the reason for low accident rates in this industry. Another important factor is government and international regulatory agencies, as well as independent industry and user associations, such as airline pilot associations, the Flight Safety Foundation, the NASA Aviation Safety Program, airline passenger associations, and so on. Nearly all aspects of operations are regulated and audited. Programs for reporting near misses and deviations from defined procedures have been enormously successful in getting feedback before accidents occur. Investigation of accidents has been an important component of reducing accidents in commercial aviation, particularly now that accident rates have been driven down so low. Investigations are remarkably thorough, with information gathered about every component of the accident. New components have been added to aircraft to assist in investigations, such as black box recorders, cockpit voice recorders, and other types of aircraft instrumentation. There was a time very early in the development of aviation when the approach known as fly fix fly was common, but that was before the development of aerodynamics and the science behind flight. Before much is known scientifically about a new technology, the only way to learn is through experimentation. But it is not the primary approach today, except for very new concepts. Such experimentation is not done while endangering the public's lives, but instead may be done using test pilots and various types of experimental rigs, such as wind tunnels. The efforts put into investigation of accidents today is a result of the success of all the other things that have been done to increase safety in this industry. Accidents now occur because of changes in the design, operations, and environment of aircraft, and when the assumptions underlying the original design and even oversight activities are no longer held. We can try to anticipate that the assumptions are changing, but when the change is gradual and not planned, we are often left to gather this information after a tragedy.